Swayam Prabha. Digital India. Educated India.
Till the last lecture, we have been doing the analysis of rotor bearing system in great detail for torsional vibration and transverse vibration, and mainly those analyses were concerned with the finding natural frequency, mode shape, and unbalanced force response or forces due to other sources. How to get the response for force response for that. From today we will start another topic on instability on the rotor system, but before going into the actual subject of instability, we would like to introduce the fluid film bearing concept and the rolling element bearing concept. Especially the fluid film bearing, their main source of instability in the rotor system, like force response always will be there in the system due to unbalance. On the same lines, this instability is the main cause of this instability is due to the fluid film bearings. So, in some detail we will try to see how the rotor dynamic coefficient of these bearings can be obtained and how it will be affecting the instability. That will be learning in the subsequent chapter. So, basically in this lecture we will concentrate on the bearing, hydrodynamic bearing and rolling bearings, and how we can able to get the rotor dynamic coefficients from this. Like for bearing, we will introduce the Reynolds equation for hydrodynamic bearing, and for short bearing approximation or long bearing approximation, how we can able to solve this particular partial differential equation in closed form we will see, and also we will give brief idea about if the bearing is finite, how the Reynolds equation can be solved using finite difference method. A brief of the rolling element bearing stiffness. Generally, rolling bearings are highly nonlinear in nature in stiffness, but we will try to obtain the stiffness, linearized stiffness using simple procedure. So, starting with the hydrodynamic film lubrication in particular bearing, there are three category of bearings we have in the industry. It's a very abstract definition of the three kind of bearing, like hydrodynamic bearing, in which one surface is stationary, another is moving tangential to it. In between this there is a fluid, and generally we will be having some kind of converging area, and because of this motion the pressure will develop in the converging area due to that this particular body will be lifted up from the there will not be metal to metal contact between the moving body and the stationary body. Another kind of is the squeeze film. So, in the squeeze film lubrication, generally the force is in this direction or the motion is in this direction, and whatever the lubricant is there in between the two body will be getting squeezed out during the motion, and this generally gives some kind of damping into the system, but not the stiffness as such. Apart from that, we have hydrostatic lubrication. In this, generally the separation of the two bodies take place because of the pressurized fluid from all sides. So, because of this pressure, this body will get lifted and will be having no metal to metal contact between these two bodies, between which the motions we expect. So, this is the three basic concept by which we separate the two bodies so that there is no metal to metal contact them. Focusing on the hydrodynamic bearing. Hydrodynamic bearing, the most simple hydrodynamic bearing is the plain cylindrical bearing, in which the bearing cavity is circular, and if you see from side it will be cylindrical in shape. So, shaft goes inside this, and there is a very small clearance between the shaft or the journal and the bearing. So, main important thing in this is this particular journal bearing, the shape is circular, and as such the lubrication comes and goes from the sides, or sometimes we provide some kind of groove onto the this bearing. Another kind of bearing is the longitudinal bearing. The shape is circular, but generally we provide the groove at these. So, you can able to see the whole axial length of the bearing, there will be groove and the lubricant will go from that side. There is another kind of bearing in which the shape is again circular, but there is a circumferential groove which is there at around midpoint of the length of the bearing. So, all over the circumference there will be groove which will give lubricant inside the bearing, so that there is enough lubrication between the journal and the bearing. Apart from that, we have partial arc this bearing, in which generally you can able to see this is basically the circular bearing. We have cut some portion of this and some portion of this, and the remaining arc we have joined together. So, this is that partial arc, and the lubrication grooves are here or on the top surface of the circumference, not at the bottom, because generally the pressure develops at the bottom. So, if we provide lubrication grooves there, the chances are there that lubricant will go out from the bottom grooves rather than coming inside the bearing. Then we have lemon bore bearing, in which there are two lobes. You can able to see there are two arc and basically this is elliptical shape, and grooves are there at these two places from where the lubricant go inside the this bearing. Then there is three lobe bearing. So, you can able to see three bearing arcs are there, and the lubrication is provided through this a portion of the grooves. So, extension of this is 4 lobe. So, 4 arcs are there, and at each corner there is a provision for the providing the lubrication to the bearing. Then there is offset halves. So, you can able to see this particular 2 arcs are there, but they have been offset by some amount, and there is a grooves here, so that the lubrication can go in this. In this particular case, you can able to see that the rotation can take place of the journal in one direction, but opposite is not feasible, otherwise this will obstruct the motion. Why we provide different shapes is a question, why we are going from cylindrical to various shapes. So, generally in a stability point of view, the plain cylindrical bearings, journal bearings are most sensitive to instability, and to avoid that generally we provide different kind of shapes, and most stable bearings are the tilting pad bearings. So, you can able to see that these are the pads which can tilt about its pivoting point, and journal rotates here. So, depending upon the requirement, these pads can take different orientation, and this is the most stable. So, highest stability of the rotor system will be there with the tilting pad journal bearing. So, now we will be looking into the Reynolds equation. Before looking into it, the assumptions of this, let us see how the journal and the bearing occupy the position at some operating speed. So, this is the journal. This is basically circular shape. So, this is the bearing which is fixed, let us say, and this is the journal, and this clearance is generally will be very less, of the order of microns, but I have just exaggerated here so that I can show various parameter on this. So, this gap will be so between the journal and the bearing, lubricant will be there, and this gap will be of order of microns, and you can able to see this B is the journal, the bearing center, C is the journal center. Between these two distance is a eccentricity, and the angle, if we join this line, bearing center and the journal center line with vertical, that angle is called attitude angle. So basically the eccentricity, radial eccentricity ER, which is nothing but Bj, and this altitude angle defines the position of the journal. And in this particular case, you can able to see the journal is rotating in this direction, and basically it is pumping the fluid which is here, because the fluid will get trapped here and it will pump in this narrow region, and because of this continuously converging shape, we will see that the pressure will develop, and that will allow the bearing and the journal to separate, and there will be very high pressure in this region, and that will basically sustain the weight of the journal or any other force which is there onto the journal. And at any position, the film thickness is given by this. So this h is the film thickness. Use the velocity of the journal, and capital R is the radius of the journal, and this particular line which is joining the bearing axis and the shaft axis, this will be the reference position when we want to measure the circumferential angle or maybe circumferential length S. If you want to measure what is the distance in the circumferential direction, this will be the reference line for us, reference position for this. So basically now we can look into the Reynolds equation. Will not derive, but we will just show the Reynolds equation and what are the terms in it has. So basic assumptions of this particular while deriving the Reynolds equations are: film thickness is small as compared to the journal dimensions, journal is cylindrical, and bearing surface is without local distortion, journal axis is parallel to the bearing axis, inertia of fluid in film is negligible. So this is another important assumption which we make: inertia of the fluid we neglect, fluid film unable to sustain subatmospheric pressure. So wherever negative pressure is there, this will not be cavitation may take place. So we are not considering that cavitation aspect here. Fluid pressure is atmospheric in supply, drain, and at regions where the fluid film is broken or cavitated. So wherever cavitation possibilities are there, we are assuming that is atmospheric pressure is there. A laminar flow in the bearing fluid film, viscous shearing loss in the clearance region outside the pressure field, and this space is taken as partly filled with fluid. No frictional loss from the fluid in the groove or drain spaces adjoining journal. So these are the some of basic assumptions. Fluid is simple Newtonian fluid with viscosity independent of the shear rate. The viscosity and the density of the fluid is constant throughout the bearing. So these are the basic assumption deriving this Reynolds equation. This is basically partial differential equation. You can able to see P is the pressure inside the fluid, and S is the circumferential direction, and Z is the axial direction. So axial direction is the Z axis direction. So pressure variation can be there in the axial direction or the circumferential direction. Rho is the density of the fluid, H is the film thickness, nu is the viscosity. Here velocity, journal velocity is u. Also, yeah. So all the terms. So this is time derivative. So if there is some dynamic force in this, so this term will be there. If we are considering the steady state condition, then this term will be we can neglect. Then once we have this Reynolds equation, let us see the concept of the linearized coefficient. Basically, this Reynolds equation gives the pressure from which we can fluid pressure, from where we can able to get the fluid forces by multiplying this pressure with the area of the surface of the bearing. So this particular plot is basically plot of the center of the shaft with speed, how it changes. So at 0 speed, so this is the bearing center, this is the shaft center at 0 speed, but when the speed is increasing, the shaft occupies some inclined position, and this is the point where at a particular speed journal occupies at some inclined position, and in the previous figure we have seen that position we are describing by the radial eccentricity and the altitude angle. So this is the equilibrium position of the shaft for steady state force. So if there is a dynamic force, then the shaft will be oscillating about this point, and the linearized stiffness are defined the disturbance of the journal from this equilibrium position when we are disturbing by a small amount, then whatever the change in the fluid pressure will define these linearized coefficients. So basically earlier we have shown in the previous lectures this kind of linearized coefficients. So this is the fluid pressure, and these are the static forces in the vertical and horizontal and vertical direction, and these are the terms basically for Reynolds equation, because we are not considering the fluid inertia. So these terms are generally present when we have very high velocity of the rotors. So these are called mass coefficients. So this stiffness, damping, and mass coefficient. So Reynolds equation does not take care of this particular property of the fluid. So in this particular case, you can able to see how the stiffness, damping, and mass coefficients have been defined. So basically, change in the fluid pressure for a given displacement disturbance or velocity or acceleration disturbance, these property have been defined. So this is basically because in the Reynolds equation is having two variables. There is one is the circumferential direction, another is in the axial direction. So we can able to see that if we have this cylindrical shape of the cylinder, and if we cut this in one portion, if we cut from here, and if we unwrap it like this, so you can able to see that we will get a rectangle shape of if we unwrap this, and let us say this is circumferential direction, that is S, and this is axial direction, Z. So this particular inside surface of the bearing, generally we will seek the solution of the pressure at each and every point on this two-dimensional space, because the partial differential equation is two-dimensional. One is in the axial direction, another is in the circumferential direction. So unwrapped portion of the bearing surface is this, in which this is the circumferential direction from 0 to 2 pi r, and this is the axial direction of the bearing, and in the Reynolds equation defines the pressure in this region, which is function of S and Z. And if in the previous figure here, if we see the film thickness is maximum here and minimum here. If we cut the film thickness here, and if we unwrap this, we will get something like this, in which this is the maximum film thickness H, which is the reference point for angular displacement 0, theta is equal to 0, and then is minimum here, and then it again become maximum. So basically this point and this points are at the same point, because after 2 pi again these two will meet. So this is the unwrapped the film thickness along the angular position, how it changes with the angular position, this film thickness. So now we'll try to solve the Reynolds equation using finite difference method in this region. So basically we need to put various grids and we will seek the solution of the pressure at various grids. So, before that let us see if we want to solve the partial differential equation in closed form. So, using two basic assumptions, one is short bearing approximation, another is long bearing approximation, we can able to simplify that Reynolds equation. For short bearing approximation, short bearing means this is the axial length of the bearing is short as compared to this one. So, if bearing length is short, we will see that the pressure because here it is atmospheric pressure, here also it is atmospheric pressure. So, at the center, up to center, there will be continuous variation of the pressure will be there. So, that means the variation of the pressure in the axial direction will be there in the short bearing, but if you see in the circumferential direction, the pressure variation will be relatively less, and this can be ignored. So, for short bearing, the circumferential direction pressure variation we ignore it. So, the Reynolds equation will be containing only derivative with respect to z. So, that will be a ordinary differential equation, and that can be solved. Another approximation is the long bearing approximation, and this you can able to see because the length of the bearing is so long that the variation of the pressure will not be there in the axial direction. Slight variation will be there at the end only, but if we see in the circumferential direction, lot of variation will be there as compared to the axial direction. So, in this particular case, we can able to neglect the variation of the pressure with respect to z, and again in this particular case, the Reynolds equation will be only differentiation will be with respect to circumferential direction s, and again it can be solved in the closed form solution. I will be providing the final solution of the this stiffness coefficient and the damping coefficient for the short bearing approximation, which we can get from the pressure as discussed in the previous slide, that once we know the pressure, we can able to get the fluid forces, and change in the fluid forces defines these coefficients. So, they can be obtained using this simplified Reynolds equation. So, we already seen the short bearing approximation, how so these are okay. So, apart from the equation, obviously when we need to solve the partial differential equation, boundary condition need to be satisfied. So, the previous slides are basically description of these boundary conditions. So, I am explaining the boundary condition in the figure itself rather than going into the text. So, you can able to see the first boundary condition, which is full Sommerfeld condition. Full Sommerfeld condition is this is the lubrication pressure and this is the circumferential direction. So, at 0, that means where the maximum thickness of the film is there, pressure is 0, this is the assumption, and when we are going up to the other end of this, again it becomes 0, but in between this around pi, again there is a pressure 0. So, this is this full Sommerfeld conditions, but this negative pressure will give cavitation. So, this boundary condition is not the feasible ones. So, sometimes or most often we go for the half Sommerfeld condition rather than the full one, in which we take the boundary condition up to this only, we do not go up to this. So, wherever the pressures are negative, we take them as 0. So, only half Sommerfeld conditions is considered. Another condition is, or alternative is the Reynolds condition, which is more practical. In this particular case, at theta is equal to 0, where the maximum thickness of the film is there, pressure is 0, but here after pi, wherever the pressure gradient is 0, we take P is 0. So, you can able to see wherever the pressure gradient is 0, P is 0, and so this particular boundary condition we need to use in the solution of the Reynolds equation, either using short bearing approximation or long bearing approximation, or even for this finite bearing approximation, which I will be describing subsequently. So, for short bearing approximation, I am giving the linearized coefficient directly without solving the equation as such. Here, this is the clearance, radial clearance, this is the weight of the journal, this is the stiffness coefficient. So, basically these are non-dimensional stiffness coefficients are defined. This is damping, non-dimensional damping. Again, this has been defined like this, and in this particular case, this particular expressions we have taken from Smith's book. So, you can able to see that we have explicit form of these stiffness coefficients. So, you can able to see this epsilon, I will be defining what is epsilon, q function of epsilon I will be defining. So, basically if we know the epsilon, these stiffness coefficients can be calculated. Similarly, the damping coefficients, they can be calculated. The one point is there that the stiffness coefficient, the cross coupled stiffness coefficients are equal, but not the this stiffness coefficient. Only the damping coefficients are equal, and generally the instability comes into the rotor because of this cross coupled stiffness, this and this one. So, they are not same, and mainly the instability comes because of these coefficients. So, here I have defined the q capital, which is function of epsilon, and epsilon is eccentricity divided by the radial clearance. So, you can able to see if we know the epsilon, we can able to calculate these coefficients. That means, if we know the eccentricity of the rotor, we can able to calculate these coefficients. Generally, we obtain these bearing property in terms of the Sommerfeld number, which is defined like this, where d is the diameter of the bearing, L is the length of the bearing, n is the revolution per minute, that is yes, this is the RPS, and this is revolution per second, and this is weight of the journal, this is radius of the journal, and this is the radial clearance between the journal and the bearing. So, this is basically revolution per second, n is the revolution per second, this is capital N. Now, this Sommerfeld number we can able to express in terms of this epsilon, which is nothing but the non-dimensional eccentricity. Now, we can able to see that this Sommerfeld number is dependent upon the bearing operating conditions, as well as the dimensions of the bearing and the property of the bearing lubricant. Now, for a particular bearing at a particular speed, we know we will be knowing the Sommerfeld number of that, and from this equation we need to find out what would be the epsilon value for that particular Sommerfeld number. So, basically if we plot these two, Sommerfeld number with the epsilon, we will get a curve like this. So, Sommerfeld number and eccentricity ratio epsilon. So, this is the curve. So, for a particular bearing we can able to calculate the Sommerfeld number. From this plot we can able to interpolate what will be the epsilon value for that particular bearing, and once we know the epsilon, we can put in the stiffness and damping coefficient expressions to get the property of that. So, this is the procedure generally we follow for calculating the stiffness and damping coefficient of the bearing. Basically, this is the same procedure which I described, how we can able to get the bearing property using the Sommerfeld number and the expressions which are given previously. These are the plot of the Sommerfeld number, the stiffness variation and the Sommerfeld number. So, for various Sommerfeld number we have summarize this non-dimensional or dimensionless stiffness coefficient. So you can able to see the variation of various kxx, kyy, kyx. This particular kxy, it becomes negative, so it has been shown in this region as dotted line. So this is the negative, because this is a log semi-log plot. So there we cannot able to plot the negative value. So we have taken absolute value of that and are indicated by dotted line as these are the negatives value of the stiffness. Similarly, the damping Cxx, Cxy and Cyy, and these two are same, cross coupled stiffness damping are same, but not the stiffness as we have seen in the previous plot. Now we will see how we can able to solve the partial differential equation, this Reynolds equation using finite difference method. So brief outline of the method will be explained, and for this particular case, as we have explained previously, this is the once we cut the bearing and unwrap it, this will be the bearing inner surface. So in finite difference method, we need to make a grid, and we will be seeking the solution at these nodes. So basically you can able to see, if we take one particular node, this is that particular ij node, and neighboring nodes are like this one is I plus j, I minus I comma j minus 1, this is I plus 1 j, and this is I minus 1 comma j. So we will be predicting the node node pressure here with the help of these neighboring nodes, and if we require further points, we can able to consider in between, and for that particular case the node description will be like this. Now the Reynolds equation we can able to write using the partial differential equation like this. So each and every term, because this was second derivative, so we can able to express the derivative with respect to S of the pressure like this. This is the film thickness. Similarly, the other variation with respect to Z, which was also second derivative, so that will take this form. Right hand side, we have removed the time dependent term. We are considering the steady state condition. So that is the variation with S was there of the second derivative, first derivative. So only this term will be there. So these equations are now we can able to arrange such that we can able to club the terms containing like pressure variation at ij in one place, I comma j plus 1 at another place, like that. So all 5 node positions pressure terms we have collected and we have expressed like this, and this can be written now in a more regression way. So the pressure at the ij we are predicting with the help of neighboring 4 nodes, and these various constants are known quantity, either film thickness or the circumferential distance or radial distance or axial distance. So this equation is very important. So you can able to see that we are predicting the pressure at the central node by 4 neighboring pressures, and we can able to write ij for the whole domain. So starting from one corner to another corner of the whole grid. So basically we will be getting several equations like this. They will be simultaneous equations, and we need to solve them one by one. So we have predicted this pressure with the help of the neighboring pressures, and so basically these recreation equations we need to solve iteratively. That we will see the procedure, but let us see this particular point which is there in the unwrapped position. If you want to see that particular point in the bearing, this is the point. The position of that angular position we are representing by psi. So this particular pressure, if we multiply the area, this particular area, so we will get the force, how much it is exerting onto this bearing. because this is the pressure at this point. If we take half of this, and so if multiply by this area, so that will give how much force which it is giving in the radial direction this particular fluid. So this is the way we will be obtaining from pressure the force value, and then we can able to take the component of these forces which are in different direction, in the horizontal direction, vertical direction, and then we can able to see their force balance. So we can able to see this is the force balance in the horizontal direction. So component of that pressure into the area, and so this is the force and this is the component in the horizontal direction. Similarly, if we take sine of that psi, then we will get the horizontal direction, vertical direction force. Basically in this the general weight which acts in the downward direction, but there is as such no horizontal force. So basically we need to find out these pressures iteratively using the previous recursion relation, such that this force is equal to the weight of the journal, but this should be 0 because there is no net force in the horizontal direction. So this is the basically outline in which this I already explained. So basically in this particular case we need to obtain the pressure at each and every node, and we are obtaining from neighboring nodes, and once we obtain at that, we can switch over to a next node. And in this particular case, one important thing is, if we are predicting the pressure negative at any point of time, then because Reynolds equation does not take care of the negative pressure, so we need to put that pressure equal to 0 and proceed. So we will see that iteratively we will be solving the pressure at each and every node from one end to another, and once we are done once, again we can come back to the original position. So we will be keep repeating this till we will get no variation in the pressure. That means in the subsequent iteration the variation in the pressure is negligibly small up to the desired decimal point. And once we get this particular pressure variation, then we have seen that we need to check that the horizontal component is 0 or not of the whole bearing, and the vertical component of the pressure is equal to the weight of the bearing or not. If that is the case, then we have reached the solution point, and from there then we can able to we can able to get basically position of the eccentricity and the altitude angle. So for that, let us see. So basically we need to follow this procedure, and for various values of the epsilon. That means we need to, once we have got the convergence, then basically we will be getting the equilibrium position of the journal. That means eccentricity and the altitude angle, and we can able to find out various combinations of this. That means the altitude angle and the eccentricity. So in this particular plot, we can able to see that the Sommerfeld number and this eccentricity ratio variation have been provided for different L by D ratio. So for finite bearing, we can able to combine this kind of non-dimensional parameter, because if for a particular bearing we can able to calculate the Sommerfeld number. From there we can able to predict the eccentricity ratio. So this basically gives the equilibrium position of the bearing. So you can able to see here, even if we want to plot the variation of the path for different L by D ratio. So this contains both the eccentricity as well as the this altitude angle. So this is having more information regarding the bearing equilibrium position. So this was again I am repeating. This was very brief description of how we can able to solve the Reynolds equation using finite difference method or using short bearing approximation, how we can able to get the coefficients. Now we will introduce very briefly the rolling element bearing and how we can able to get the linearized stiffness coefficient from this. So in this particular case, you can able to see this is a ball bearing, this is a roller bearing. In this, the shape of the rolling element is cylindrical. Here it is in the spherical shape. The close view of the bearing is that this is a rolling element ball, and there is a inner raceway, outer raceway. There is a groove over which this particular rolling element roll. So you can able to see this groove, and these rolling element bearings are put in a cage kind of thing that is called separator or retainer. So they separate these ball with each other so that they should not collide. And other dimensions like bore where the shaft will go, or the outer diameter. So the housing dimensions we need to make of the size so that the bearing can go in the housing. This is the width of the bearing. So this is a basic nomenclature of the ball bearing. More close view of the this particular ball bearing, you can able to see if we join this circle, this ball centers, there is a circle, imaginary circle, which we call it as a pitch circle. Diameter of that is pitch diameter, and this is the ball, and these are the grooves, and this ball they roll over inside this groove, and these grooves are having different radius as compared to the ball. Generally this radius is more so that the ball can freely roll over these grooves. Apart from this, some more dimensions are there. This inner groove diameter, outer groove diameter. Now let us see various kind of ball and roller bearing types. So that means this is a deep groove ball bearing. This is angular contact ball bearing. In this particular case, the angle of contact of the ball bearing is large. We will see what is the contact angle in the subsequent slide. A double row angular contact ball bearing. So 2 rows are there. This is self-aligning bearing. So in this particular case, the inner ring can tilt with respect to the outer ring by large amount. Then this is the thrust bearing. Generally the load comes in the vertical direction, so that they take the load here. So load comes like this in this particular case. This is cylindrical bearing, cylindrical roller bearing. So shape of the rollers are cylindrical. Double row cylindrical bearing, taper roller bearing. So this is frustum of cone, or double row spherical bearing. So the shape of this contacting surface are spherical in shape, similar to the cylindrical bearing, but curvature are more at on the contacting surface. This is the needle bearing, in which the length is relatively long as compared to diameter of the bearing. So this is the basically load zone in rolling bearings. So this is the inner ring, let us say, and when we apply the load into the inner ring or outer ring, generally not all the rolling elements take the load. Partly some of the rolling element take load, and how much is the load zone is defined by the clearance. So if clearance is positive, then we will see that the load zone, which is defined half of this total angle, will be less than 90 degree. So only the rolling elements which are within this area will be loaded. If there is no clearance, then this load zone is 90 degree. That means total 180 degree. Here whatever the rolling elements are there, they will take part in the load. They will be free, they will not take any load. Here also the rolling element which are here, they will not take any load. But if we have negative clearance or the preload, if ball are preloaded, then we will see that the contact zone is more than 90 degree, and most of the rolling element take the load. So generally if we are providing the preload, we find that we have more number of rolling element taking part in the load sharing. So generally using the Hertzian contact theory, we define the load versus deformation relation between two contacting bodies, and for point contact, that means two spherical contacts, we have this relation. So you can able to see this is the load, this is the deformation at the contact point or point load. This is the exponent 3/2 for ball bearing, that is point contact. This is the load deformation constant, which depends upon the geometry of the bearing and material property of the contacting bodies. This can be written like this. Now this is for single point contact at one of the contact. If we have in the ball bearing, we have 2 point contact, one at the inner ring and at the outer ring. So these two deformations, the total deformation can be defined as summation of these two, and the previous expression can be substituted for inner contact and outer contact. So it can be simplified like this, because load is same. So because load transmitting is same, so we will get this expression. So basically this is some kind of equivalent the load deformation constant for the 2 point contact, which is defined like this, or inner contact and outer contact are these. Now this particular approximately was given by Palmgren like this, where dB is the diameter of the ball and F is given as the curvature ratio, which is given like this, where R is the groove radius. In this figure you can able to see the groove radius clearly. So this is the radius of the groove, which is groove radius. This is the deep groove ball bearing. If we apply axial load, this inner ring and outer ring, they shift relative to each other, and now you can able to see the point of contact of the ball with the races are here. So this is the line where the load will be acting in this direction, because point of contact is here, and the angle of this with respect to the vertical is called contact angle, and this distance is the end play. P is the end play. So this happens because of the clearance in the bearing. So this contact angle is important because it defines how much axial load it can take. Similarly, for roller bearing, similar expressions, only the exponents are different, and for 2 point contact this will be defined like this. Approximately this is given as this, only the effective length of the roller is incorporated in this. This is the roller, and you can able to see at the ends we have chamferings. So effective contact will be in this region, and that is we need to consider in the calculation of this. So this is the deep groove ball bearing. We are applying a external load here, let us say to the inner ring, and so ball are getting compressed. So this is the load zone. Because of clearance, the load zone is less than 90 degree. Now one particular ball which is at the xi angle, this will, in this particular case, this particular rolling element, which is let us say just below the direction of the load, is having let us say xm displacement. So you can able to see the inner ring is getting displaced in the direction of the load by xm. So this particular rolling element which is at the xi angle will be having displacement xm into cos xi, and similarly this xi can be this bearing or this ball or any other angle. So basically you can able to see that actual deformation of the ball will be displacement of the ring with respect to the let us say inner ring with respect to the outer ring minus the clearance, because the clearance we cannot define that as a deformation. So displacement of the inner ring with respect to outer ring center minus clearance will be the deformation of the deformation. And as we have seen in the previous slide, the deformation at an angle xi of the ball will be xm cos psi minus clearance, because in that direction also radial clearance is Cr. So this is the deformation at any angle of the ball, and if we keep that deformation is equal to 0, that means deformation will be 0 only when the ball is outside the this load zone. So here, so basically putting this equal to 0, we are trying to find out what is the angle xi for which there is no deformation. So this will give us the load zone relation, and this load zone relation we can able to see for 0 clearance we will be having pi by 2 load zone. Now now we can able to take the equilibrium of a ring. That means all such forces because of the ball at various angular positions xi, we can able to sum up for all the rollers. If these rollers are outside the contact zone, those terms will be 0. So that should be equal to the external applied load, where z is the number of rollers. So basically for a given bearing we can able to choose this particular displacement. From that we can able to get various displacements at various ball locations, and from there we can able to get the contact forces, because once we know the this deformation, we can able to use Hertzian contact relations to get the contact forces, and these contact forces then we can add it up, we can add the component of that in the radial direction and check whether that is equal to the external load or not. If not, then again we need to give another this displacement. Basically here iteratively we are trying to find out what should be the displacement for that particular given radial load. If this displacement is not equal to the actual one, this will not satisfy, then we need to repeat this iteration till we get the close value of the xm for which the bearing is having that much displacement. In rolling element bearing, for a given force, obtaining the displacement of the inner ring with respect to outer ring is iterative procedure, and if we can able to obtain for a particular load how much the deformation, and if we vary the load and again what is the change in the change in the deformation, then basically what we are obtaining a variation of the load with displacement, and from this we can able to get the stiffness term. So for this I am giving the expression of the stiffness of the rolling element bearing. So first one is for ball bearing. So this particular stiffness expression is this one. So you can able to see this is a number of rolling element. This is the load displacement constants. This is the deformation or displacement of the inner ring with respect to outer ring. This is the clearance. This is a factor which we have used for ball bearing. Basically it gives a relationship between the actual force which is we are applying, like if we are applying to the bearing Fr force. So what is the force Fm, the ball which is just below the in the direction of the radial load is taking this particular factor defines that. So let us see that particular expression. So this is the force which a particular ball which is just below the radial direction of the load is there. C1 is the constant which is given as 4.37 for ball bearing and 4.08 for the roller bearing. Z is the number of roller. So this expression we have used in this calculation of the stiffness, and this is coming from the exponent of the Hertzian contact for ball bearing and roller bearing. So these two expressions can be used to obtain the linearized coefficient of the stiffness. Yeah. So these two expressions can be used to obtain the stiffness coefficient for the ball bearing and the roller bearing directly. And for more detailed calculation of these load deflection calculation, people can refer to Harish, that is 2000 book on rolling bearing analysis, rolling element bearing. analysis book. So, because the detail is not possible to cover in this particular in single lecture, so I am referring this particular book, which itself is 1000 page, for more detailed analysis of the rolling element bearing. In today's lecture, we covered very brief idea about the fluid film bearing and the rolling element bearing. It is not possible to cover the concept of these two bearing in a single lecture, but just to have idea of what kind of bearings, fluid film bearings are there, what type of rolling element bearings are there, and especially how we can approach the calculation of the rotor dynamics coefficient. That was important, that I try to outline in this, but for more detail, obviously there are dedicated books on tribology that can be referred for calculation, more detailed calculation of this kind of bearings. For bearing designed to carry vertical loads, only for example the gravity load, the relationship between the eccentricity ratio and general attitude angle phi may be determined by investigating different value of phi for a given value of epsilon until the value of Fh, that is a vertical horizontal force, is found to be 0. So, if gravity is the only load onto the rotor, so Fh if it becomes 0, then we can have the combination of the eccentricity ratio and phi for the rotor for that particular operating condition. For example, once we choose an arbitrary value of epsilon and phi, then corresponding film thickness can be obtained, since phi and epsilon and phi determine the position of the shaft with respect to the bearing bore. Using iterative procedure or using all simultaneous solution procedure, by solving the finite difference equation simultaneously, the pressure distribution is obtained by putting negative pressure equal to 0. So, whenever we are obtaining negative pressure, we are keeping that equal to 0. Resultant forces of the journal is obtained by using previous equations for horizontal force equal to 0 and vertical force is equal to weight of the journal. If the above force conditions are not satisfied, then different value of phi could be chosen until the force conditions are satisfied up to the desired accuracy. So, basically here we are trying to find out for a particular epsilon value what should be the phi value to satisfy these two conditions. When this process is completed, it is found that because the Reynolds equation is a continuous function, the final pressure distribution correspond to Reynolds boundary condition with the constraint of this gradient is equal to 0, which we described earlier. At trailing edge of the lubricant film, automatically this is scattered forward. Above procedure can be repeated for different value of epsilon to get relationship between epsilon and phi for a particular bearing at different operating conditions. This trial and error method enables corresponding value of epsilon and phi and Sommerfeld number as to be found. So, with this we can able to plot the eccentricity ratio with Sommerfeld number, which we defined earlier. So, basically it depends upon various operating parameter of the bearing, including speed. For various geometry, we can able to plot these relations. Even we can able to plot the epsilon and the altitude angle for various geometrical conditions of the bearing, like for L by D ratio 0.5, this is the curve, and the second curve is for L by T, L by D is equal to 1. If the fraction of net radial load applied that is transmitted through the rolling element directly in line with the applied load is known, then the resulting inner ring displacement may be calculated directly. So, we have this is the bearing, inner ring, and let us say this is the rolling element which is here. So, if you are applying a radial load onto the inner ring, and this particular roller or ball which is just below this particular radial load. So if we can find out what is the load shared by this particular rolling element as compared, because this load changes with the angular position of the ball. So if let us say the load shared by this particular rolling element is Fm, so if we can obtain what is the load shared by this particular rolling element, then it is easy to obtain the load distribution and also the stiffness of the bearing. So this is the total displacement of the bearing or the displacement of this particular ball also, they will be same. So this is the deformation plus the radial clearance, and this deformation is of the ball is due to the load shared by that particular rolling element. So we can able to get using the Hurtgen relation, in which the exponent will be 2 by 3, and in this particular case C are the clearance, radial clearance of the bearing. Similarly, for roller bearing, we will be having a relationship between the deformation of the maximum loaded roller like this, in which the exponent will change, and this is the radial clearance of that particular roller bearing. The same relations is given by Palmgren. These are approximate relationship in which we neglected the bearing clearance and geometry. So the similar relations is provided based on the experiment. So these can also be used, where dB is the ball diameter, L is the effective length of the roller. So this is for ball bearing and this for roller bearing. The relationship between Fm, the maximum load which a particular rolling element is carrying, and the net radial force Fr which we are applying to the bearing, is approximately related as like this. This is also approximate formula, in which the C1 constant and Z is the number of rolling element. C1 constant is basically, it depends upon the number of rolling element, load deformation constant, and bearing clearance, and approximately it can be taken as 4.37 for ball bearing and 4.08 for roller bearing. So this relation gives directly what will be a particular roller or ball which is just below the radial direction shared that particular load. So once we have obtained this particular load from previous relations, we can able to obtain the deformation also. So for ball bearing, so in place of Fm, we have substituted this 4.37 Fr by Z in the previous relations for ball bearing. Similarly for the roller bearing. And now for particular load Fm, the deformation of that particular roller which is just below the radial direction of the external load is given by this, and they are related by Hurtgen relations like this for ball bearing and roller bearing. So when this is for one particular ball or roller. So once we have this relation, now we are defining the stiffness, bearing stiffness, which is nonlinear in nature. So that bearing stiffness is defined as the change in the radial load applied and the deformation of the that particular roller or ball which is getting maximum deformation, even that is equal to the deformation of the rolling element, that is inner raceway or outer raceway also. So basically that displacement is between, or the relative displacement between the inner raceway and outer raceway. So we can put the Fr from previous expression, so we will get the stiffness term like this, and Fm again we can able to put from previous relations which we have here. So to get the ball bearing stiffness in terms of various parameter of the bearing like clearance, this is the maximum loaded roller deformation, and this is the number of roller. This is the load deformation constant for point contact. Similarly, for roller bearing, we can able to obtain the stiffness, and this the exponents got changed, and even this load deformation constant will be different. So this is the animation for translatory forward whirl. So you can able to see that in this particular case, shaft is rotating clockwise. Also, it is whirling in the clockwise direction. So again, we can see shaft is rotating clockwise, and also the whirling direction is clockwise. So this is a forward translatory whirl. This is the animation for transverse or translatory backward whirl. In this, the shaft is rotating clockwise, but the whirling is counterclockwise direction. Again, we can see once the shaft is spinning about its own axis in the clockwise direction and is whirling in the counterclockwise direction. So this is a backward translatory whirl. This is the animation for forward conical whirl. And this shaft is rotating about its own axis in clockwise direction, but if you see end of the shaft, that is also whirling in the same clockwise direction. So that's why it is forward conical whirl. Again, we can see this animation. So shaft is rotating clockwise about its own axis, also is spinning, whirling at both ends is clockwise. This is the animation for backward conical whirl. In this, again, shaft is having same direction clockwise, but is whirling in the counterclockwise direction. So again, you can able to see this shaft spinning, and the whirling directions are different. So whenever this is the case, we will be having backward conical whirl. This is the animation for pure whirling of the disc about its bearing axis. So here disc is not spinning, but the pure whirling is taking place. This is the animation for the long rotor, in which the whirling in the forward whirl direction is taking place. So in fact, when we are having synchronous whirl, the shaft bends in particular configuration and remains in that position, and the whirl take place. So you can able to see this is a pure rotation of the shaft is taking place, because we assumed here is having tilting about its center of gravity. This is the animation for the motor and the shaft whirling. So this particular motor is whirling because it is mounted on some spring which is providing torsional stiffness, and the spinning is very fast. So here we will see the whirling and the spinning frequencies will be different. So generally this particular shaft will be rotating at very fast speed, but the whirling of the whole rotor system will be, along with the motor, will be slow. So again, we can able to see once more this animation. So here you can able to see the whirling frequency and the spin frequency will be different. This is the animation of a Jepcot rotor, in which the disc is at the center, and this particular unbalance which we have shown here is away from the bearing axis. That means we are operating below the critical speed, and because the shaft is at the center, the tilting of the shaft is not taking place in this particular case. this remains vertical during motion. But if we and this one is the another case in which we have crossed the critical speed, and in that particular case unbalance will come inside toward the bearing side. So animation, this for synchronous world. So this unbalance remains and try to rotate about the bearing axis. And the third case, this particular case in which we are at the critical speed, and at that position the unbalance is in the 90 degree with the response. Basically this will give a tangential force. So you can able to see this unbalance is always ahead of the toward the disk direction of motion. So this is the critical speed condition in which the response is in this direction and the force is this. So they have 90 degree phase difference. This is the Jeffcott rotor which is mounted on bearings, simply supported bearing. The disk is at the center. So here we will try to see the motion of the disk in which there is no tilting of the disk is taking place. So tilting of the disk is not taking place. In this particular case, that particular disk is offset by is not at the center, and we will see that there will be tilting motion of the disk also, as it will is whirling, and because of this we expect the gyroscopic couple will be acting on this particular disk, because spinning about the shaft axis at high speed, and also it is whirling, and because of the precision of the disk about its diameter, there will be gyroscopic couple. So this animation we can again able to see when the shaft disk is offset from the center, the tilting of the disk take place along with the spinning, and because of that gyroscopic couple act onto the disk.